The photoelectric effect. This is a diagram of a gold leaf electroscope. It has an insulator which insulates this zinc plate which is connected to this metal rod down here. Here we have a piece of gold leaf. If the electroscope is charged up by bringing a piece of charged polythene, for instance, in contact with the zinc lid, the gold leaf will also become charged up, and the rod here is charged up, both with the same negative charge. As like charges repel, the gold leaf sticks out, like this. If we shine ultraviolet radiation onto the zinc plate, the gold leaf drops back down to its original position, showing that the charges must have been dissipated. If, however, we use visible light, the charge is not lost and the gold leaf stays in its raised position, even if the visible light is of very high intensity. So the visible light is not ejecting any electrons. With a piece of glass in between the zinc plate and the ultraviolet radiation, no electrons are ejected. The glass will absorb the ultraviolet light. With ultraviolet radiation, even if we use an incredibly low intensity, electrons are still ejected, and that starts immediately. There's no time delay. Interference effects had shown that light behaves like a wave, and it seemed for this experiment that there was a threshold frequency below which no electrons were ejected. Ultraviolet light with a high frequency would eject electrons. Visible light with a lower frequency would not eject electrons. Now, if light was a wave, if we had enough intensity and time, the electrons should eventually absorb sufficient energy to escape. This was not seen. Low intensity ultraviolet light would take time to pass on sufficient energy for electrons to be ejected, but electrons were ejected instantly. Einstein suggested that these observations could be explained if the radiation behaved as particles, which became known as photons, with a particular amount or quanta of energy each. If an electron absorbs a photon with sufficient energy, it will escape. But if the photon does not have enough energy, the electron will not escape. We're now going to look at a very simple case. We have a piece of zinc with an electron close to the surface. This electron will need 3 units of energy to escape from the zinc. Here is a photon containing 2 units of energy, insufficient energy to allow the electron to escape. So if the photon is absorbed by the electron still cannot escape. It can't save up the energy and, for instance, absorb another photon with 2 units of energy to allow it to escape. Here we have a photon containing 3 units of energy. The electron still needs 3 units of energy to escape, so if the photon is absorbed, the electron will escape, but with 0 kinetic energy. It only just escapes. Almost immediately it will re-emit this energy as another photon. Finally, a photon containing 5 units of energy, with the electron still needing 3 units of energy to escape. If the photon is absorbed now, the electron escapes with 2 units of kinetic energy to spare. Basically the 5 units of energy of the photon minus the 3 units needed to break it free of the zinc leaves it with a surplus of 2 units of energy, which appears in the form of kinetic energy. Einstein said that the photon energy E is equal to h times F, where h is Planck's constant, the tiny number of 6.63 times 10 to the minus 34 joule seconds. F is the frequency of the radiation in hertz. As the speed of light in a vacuum c is equal to frequency f times wavelength lambda, we can rearrange and substitute for frequency in this term to give photon energy E is equal to hc over lambda. H Planck's constant, c the speed of light in a vacuum, 3 times 10 to the 8 meters per second, and lambda the wavelength of the radiation. Einstein came up with the photoelectric equation as HF is equal to phi plus E K max. This equation simply means that the energy of the photon, HF, on this side of the equation, is equal to the energy needed to release the electron, also known as the work function phi, which appears here, plus the kinetic energy of the released electron E K max, which appears here. In the very simple case of the ejected electron previously, I had the photon energy HF as being 5 units. The work function phi was 3 units, the kinetic energy of the ejected electron 2 units. Obviously in real cases the numbers would be rather more complicated. Here I've written again Einstein's photoelectric equation, which I will rearrange to this format. This now links up to the general equation of a straight line, y equals mx plus c. So if I plot the kinetic energy of the ejected electrons as my y term, Planck's constant will become the gradient m. If I plot the frequency as the x term, and minus phi, minus the work function, will become my y-intercept c. So plotting a graph with kinetic energy of the ejected electrons on the y-axis, frequency of the radiation on the x-axis, I'll get a line something like this. The gradient will give me Planck's constant h. The y-intercept gives me minus phi, the work function. The x-intercept here gives what's called the threshold frequency, f0, which is the frequency of radiation below which no electrons will be ejected. Different metals have different work functions and therefore different threshold frequencies. Increasing the intensity of light falling on the metal would mean more photons per second landing on the metal, and so more electrons emitted per second. The greater the number of electrons passing a point each second, the greater the current. So the current from a photocell is proportional to the intensity of the radiation. If we double the intensity, we double the number of photons, double the number of electrons released, and therefore double the current. If the frequency of the light is unchanged, a greater intensity will mean more electrons, but each with the same maximum kinetic energy as before. Only an increase in the frequency of the light could increase the maximum kinetic energy of the electrons.